And for our last section here, we're going to talk about chemical stoichiometry and gases. We've talked about stoichiometry before when we were talking about balanced equations and calculations we can do with balanced equations, the different types of chemical reactions. We've done titrations, and we've done molarity conversions, as well as gravimetric analysis equations, all of these using stoichiometry or mole-to-mole ratios. So I'm going to write that here because we need to remember mole-to-mole ratios. So it's the quantitative relationship between reactants and products and chemical reactions. We have looked at measured quantities of reactants and products of solids and solutions, and the same can be applied to gases. So let's look at the example. Consider the following balanced equation. Determine the volume of oxygen gas formed from the decomposition of 5.36 grams of mercury oxide at a pressure of 0.975 atm and 23 degrees Celsius. In this problem, we are going to combine our knowledge of mole-to-mole ratios with our new knowledge of PV equals nRT, the ideal gas equation. Because if I want to find the volume of a gas, and I'm given pressure and temperature, we can use the mass of one reactant and convert to moles of the gas. Okay, we know how to convert from one reactant to a product. We've done that before. Now we're going to use that mole of product, and we're going to plug it into our PV equals nRT to solve for volume. So I have a little kind of chart here, or some steps here for this. So the first thing that we're going to want to do in this problem is we're going to first want to convert our mass of solid to moles of solid. Okay, we know how to do that. We can convert mass to moles. We know how to do that. So let's see, we have mass 5.36 grams. And we can use the molar mass of mercury oxide, which is 216.59 grams per 1 mole. We can find that from the periodic table, that molar mass. So we'll take 5.636, and divide it by 216.59. Okay, we get 0.02477 moles of HGO. I can't use this value in PV equals nRT because HGO is a solid. The only thing that I can plug into PV equals nRT is the mole value of a gas. So what we have to do next is use our mole-to-mole ratio to find moles of gas using the balanced reaction. So from my balanced reaction, for every 2 moles of mercury oxide that I react, I get out 1 mole of oxygen gas. So we can set up our equivalency. 2 moles of HGO give us 1 mole of O2. So we just take our mole value and we divide it by 2. To get 0.012373, and that is moles of O2. So the 0.012373 moles of oxygen can now be used in PV equals nRT. Because it's a mole value of a gas. And that's very important. It has to be the mole value of the gas itself. So we're going to use that moles. We're going to plug in moles for of gas into PV equals nRT to solve for volume. So we'll do that here in blue. So we'll take P, which is 0.975. We're solving for volume. We know moles, we just solved for that. It's 0.012373 times R. Let's see, my pressure is in ATM, so I'm going to want to use R in ATM, which is 0.08206, times the temperature, which would be 23 plus 273.15 to convert it. So we take 0.012373, multiply that by 0.08206, and multiply that by 23 plus 273.15. And then we divide that by 0.975 to isolate the volume, to get a volume of 0.308 liters. It's liters because R dictates our volume right there. So that is the volume of gas that is created when mercury oxide is reacted into mercury and oxygen gas. We get 0.308 liters of oxygen gas. Okay, so that's how we use our previous knowledge. So let's see. Step 1 was previous knowledge, and step 2 was previous knowledge. We did that in our last 2 chapters. Now we're utilizing our new knowledge here in our 3rd step of PV equals nRT in order to solve for the volume of a gas given the moles of a gas. Okay, let's try that again. In the fermentation process, yeast converts glucose, C6H12O6, to ethanol, C2H5OH, and carbon dioxide, CO2. What volume of carbon dioxide measured at 745 torr and 25 degrees Celsius can be produced by the fermentation of 10 grams of glucose? So what I want you to do for this problem is to pause your video and walk through this. I will give you the R for torr so you don't have to convert. So let's see, R for torr is 62.36 liters times torr per mole Kelvin. So there's R there. You could also convert torr to ATM. You could do that as well and use the other R. Really, whichever route you take is fine. Make sure you convert your temperature to Kelvin and follow our little steps here. Convert mass to moles, use a mole to mole ratio, and then plug in the moles into PV equals nRT. Remember, we have to get to moles of CO2 because that's the gas. The only mole value we can plug into PV equals nRT is that of a gas. So pause your video and try this problem independently. The first step we're going to want to do is convert our mass of glucose to moles of glucose. So to do that, we're going to start with 10 grams of glucose, which I'll just call glue, and we're going to divide it by its molar mass of 180.16 grams in 1 mole. So we'll take 10, divide it by 180.16 to get 0.0550506 moles of glucose. So we did step 1. Step 2, we want to use our mole-to-mole ratio to find the moles of the gas. So for every 1 mole of glucose that I put in, I get out 2 moles of carbon dioxide. So we'll take 1 mole of glucose on the bottom, so that glucose cancels, and 2 moles of carbon dioxide on top, so that we're left with moles of carbon dioxide. So we'll multiply that by 2. And we get out 0.11101 moles of CO2. This is now the mole value that we can use for step 3 to plug into PV equals nRT to solve for volume. So our pressure is 745 torr. Our volume is what we're solving for. N is what we just solved for, 0.11101. R was given as 62.36. And T is 25 plus 273, that's 298.15 Kelvin. So we take 0.11101, multiply that by 62.36, and multiply that by 298.15. To solve for volume, we then divide both sides by 745, and we get that the volume is equal to 2.77 liters with 3 sig figs on there. So that is the volume of CO2 gas produced. So again, step 1, previous knowledge. Step 2, previous knowledge. Step 3, plugging in the mole value with our new knowledge of PV equals nRT, because the mole value we get out is that of a gas, and we can measure, instead of moles of gas, the volume of gas. Let's do some more practice. Here's a problem. Given the following reaction, H2 gas plus chlorine gas goes to hydrogen chloride gas, how many liters of hydrogen gas are needed to react completely with 5 liters of chlorine gas at STP? How many liters of hydrogen chloride gas is produced in the reaction? Okay, so here's one that we have to remember from our previous lesson. We said in Avogadro's law that moles and volume are directly related. So through Avogadro's law, we can take volumes of gas and we can convert to the volume of another gas using our balanced equation, because we can say that this is 1 volume of hydrogen gas and 1 volume of chlorine gas react to form 2 volumes of hydrogen chloride gas. So we can also be given a volume of gas and need to find the volume of another gas in the reaction. In this case, treat the units of liters the same as moles. The gases are at the same pressure and temperature, so volume is equal to moles. So our mole-to-mole ratios are turning into volume-to-volume ratios. So let's try that. So let's see, how many liters of hydrogen gas are needed to react completely with 50 liters of chlorine gas? So we have 50 liters of Cl2, and from our balanced equation, 1 volume of Cl2 is equal to 1 volume of H2. So we'll say 1 liter of Cl2 is equal to 1 liter of H2. So that gives us 50 liters of H2. Now you could go about this the same way we did our previous problems, okay? You would just start off the problem, instead of converting mass to moles, you would use the liters that you start with, liters of chlorine gas, plug that into PV equals nRT, get out moles of chlorine gas, use your mole-to-mole ratio to convert to hydrogen gas, then use that moles to then plug back into PV equals nRT. But since you're plugging the same pressure and volume, pressure and temperature values into PV equals nRT, it's almost like doing the same thing twice. So you can do it the other way if that makes more sense to you, but you could also do it this way where you could just use liter to liter ratios instead of multiple ratios. Okay, so the other question was how many liters of hydrogen chloride gas is produced in this reaction? Well, we start with our 50 liters of Cl2, and we can use our mole-to-mole ratio again. Instead, this is for every 1 liter of Cl2 that we use up, we get out 2 liters of HCl. So we take 50 liters of Cl2, multiply it by 2 from our mole ratio, and we get 100 liters of HCl created. So that's a way that we can use our mole-to-mole ratios as liter-to-liter ratios. But just keep in mind that it has to be between gases. You have to be going from a gas to a gas. If you're trying to go from a solid to a gas, you cannot do it this way. Okay, let's look at this problem. Given the following reaction, when black gunpowder explodes, solid potassium nitrate, solid carbon, and solid sulfur react with each other to form nitrogen gas, carbon dioxide gas, and solid potassium sulfide. If the original mixture contains 50 grams of potassium nitrate, what volume of carbon dioxide is produced in the reaction at 0.965 atm and 23 degrees Celsius? So here we're starting with a mass of solid, potassium nitrate, and we want to find the volume of a gas. So just like we did before in our previous examples with our 3 steps. So try this problem independently. The first step in this problem is to convert from mass of solid to moles of solid. So we're going to take that 50 grams, pencils help, 50 grams of potassium nitrate, KNO3, and divide by its molar mass of 101.10 grams to get moles out. So 50.0 divided by 101.1, we get 0.49456 moles of KNO3. Our next step says to convert from moles of solid to moles of gas, and our gas here is going to be CO2. So we can go 16 moles of KNO3 produces 24 moles of CO2. So we'll take that, we'll multiply it by that ratio of 24 divided by 16, and we get out 0.74184 moles of CO2. So again, up until this point, this is all prior knowledge. We know how to go from grams to moles. of a compound, as well as from moles of one compound to moles of the other compound through a mole-to-mole ratio from our balanced reaction. Now what we do with this mole value of CO2 is what our new knowledge is telling us, which is to plug that into PV equals nRT in order to solve for volume, because we can think of gases in terms of volumes rather than moles. So PV equals nRT tells us that the pressure is 0.965 atm times the volume, which we're looking for, is equal to N, which is the moles, which we just solved for, of 74184, times R. R for ATM is 0.08206, times the temperature of 23 plus 273.15, convert that to Kelvin. So we take 0.74184, multiply that by R, 206, there we go, times 23 plus 273.15. Then we divide that by 0.965 to solve for volume, and our volume comes out to be 18.7 liters of carbon dioxide gas produced. So when we take 50 grams of potassium nitrate, we create carbon dioxide, and the exact amount is 18.7 liters of carbon dioxide. Let's keep practicing. This one we're going to work backwards. So, given the following reaction, how many grams of solid lithium must be added to liquid water in order to obtain 15 liters of hydrogen gas at 65 degrees Celsius and 2 atm? So we're now looking for the mass of a solid given the volume of a gas. So we're going to work backwards. Our first step tells us to use PV equals nRT to solve for moles of gas. Once we have moles of gas, we're going to convert to moles of solid in step 2 using our mole-to-mole ratio. And once we have our moles of solid, we can convert moles to mass using the molar mass of that solid. So the same thing that we've been doing, just now working backwards. So I want you to try this problem initially on your own. So start with our steps, our 1, 2, 3 there, and see how far you get. If you get stuck, come back to the video and we'll go through it together. The first step to our problem is to plug in our volume of gas into PV equals nRT. So P is going to be 2.0 atm. We know our volume, that's 15 liters. We're solving for N of gas. We don't know that yet, but we do know R, 0.08206. And we know the temperature, 65 plus 273.15 to convert to Kelvin. So we can solve for N by taking 2.0, multiplying it by 15, and dividing that by R, 0.08206, multiplied by the temperature, 65 plus 273. There. So just to show that we have PV equals nRT. To solve for N, I just divided both sides by RT. So we get N is equal to PV over RT. Again, if it's easier for you to rearrange the equation before plugging it in, feel free to do that as well. Okay, so we get an N value of 1.08114, and that is going to be moles of hydrogen gas, so H2. So that completes step 1. We found our moles of gas. We now want to use a mole-to-mole ratio to find the moles of solid. So we're going to take that 1.08114 moles of H2, and we want to convert that to our solid, which is solid lithium. So for every 1 mole of lithium, I get out 1 mole of hydrogen gas. So 1 mole of hydrogen gas is produced from 1 mole of lithium. So that equals 1.08114 moles there. Once we have moles of lithium, we can then use the molar mass of lithium solid, which is just from the periodic table, to find the mass. So 1 mole of lithium has a mass of 6.94 grams. So we'll take that and multiply it by 6.94, and we get out 7.50 grams of lithium. So we did step 2 with our mole-to-mole ratio here, and then we converted moles of solid to mass using the molar mass here. So we need 7.50 grams of lithium to produce 15 liters of hydrogen gas. We have a similar problem here. Given the following reaction, if 250 liters of hydrogen gas are used to reduce copper 1 oxide at STP, what mass of copper is to be expected? So we're starting with hydrogen gas here, and we're converting to copper solid. So use the same steps that we used in our previous problem, which are right here on the screen, in order to solve for the mass of copper. The first step is going to be plugging in our volume of hydrogen gas into PV equals nRT. Remember that STP tells us that our pressure is 1 atm and 273.15 Kelvin. So pressure is going to be 1. The volume is 250, which is equal to N, which we're solving for, times R, 0.08206, times the temperature, 273.15. So we solve for N. We're going to do 250 divided by 0.08206 times 273.15. So we get the number of moles to be 11.1534 moles of hydrogen gas. So that's step 1. Now we can use our mole-to-mole ratio to solve for moles of copper. So for every 1 mole of hydrogen gas, which I got from my balanced equation, I get out 2 moles of copper solid, which I also get from my balanced equation. So I'm going to take that 11 and I'm going to multiply it by 2. And we get out 22.3068 moles of copper. So that is step 2 complete. Our final step is to convert moles of solid to mass. And since we're just looking at copper solid, it's just going to be the molar mass of copper from the periodic table. So we're going to multiply this by 63.55 grams in 1 mole. 63.55, there we go. There, 63. So we get out 1,417.59 grams of copper. With sig figs, this would be 3 significant figures, so we would have 1.42 times 10 to the 3rd grams of copper as our final answer. So from 250 liters of hydrogen gas, we would produce 1.42 times 10 to the 3rd grams of copper. We can also use this concept to use partial pressures to solve problems. So when we're in an actual laboratory and we want to determine the volume of gas that can be produced from a chemical reaction like the one we just saw, the volume of the gas can actually be recorded by trapping that gas in a piece of glassware that can measure volume, right? Volume can apply to liquids, but it can also apply to gases. You just have to be a little creative about it. So we do that by trapping the gas over water. So the volume of gas produced by a chemical reaction can be measured using an apparatus like the one shown below. So here we have the reaction happening. So here's where we start. The reaction is happening here. We have KClO3 reacting with MnO2. We're heating it up. And when we heat that up, we produce oxygen gas. So the oxygen gas goes into the air, okay, and goes up the little test tube here. The test tube is attached to a tube, okay, and that tube runs underwater into a graduated cylinder. So the oxygen gas, I'm going to mark it in red now, continues through that tube, okay. The cylinder was initially filled completely with water, okay, but as the oxygen gas goes up, it's forming bubbles and it's displacing that water. So we're going to continue to displace that water with the oxygen gas that's produced from the reaction until the reaction is done. Once the reaction is complete, we can measure the volume of gas in that graduated cylinder and say that that is the volume of gas that was created from that reaction. The issue here is that these bubbles right here are going through water. And as they go through water, they actually take on a little bit of water. So the gas that's in here is actually mainly oxygen gas and some water vapor. So when gas is collected over water in this manner, the total pressure of the gas in the cylinder is the sum of the two partial pressures. Those partial pressures being the collected gas, which is in this case the oxygen, as well as the pressure of the water vapor. Now the idea here is that if we know the volume of the gas and we know the pressure of the gas, we can find the moles of the gas, which could then tell us the moles of reactant that we used in the reaction. So we have to be able to know the exact pressure of the gas that is not mixed with water. So to do that, we have to know the water vapor pressure. So the vapor pressure of water is known at various temperatures. At 0, it's 4.6. At 15, it's 13.64. At 45, it's 72, and so on. So the vapor pressure of water is going to vary at different temperatures. More water will come out of that solution the higher the temperature is. But this means if you know the total pressure and the vapor pressure of water, you can then find the pressure of the gas by itself, because P total is going to be equal to P gas plus pH2O. We know this, we can measure both of those, meaning we can find that. If the pressure of the gas is known, along with the volume of the gas collected and the temperature that it was collected at, we can use PV equals nRT to find the moles and even the mass of the gas formed. We could also go back to product and see, or go back to our reactant and see how much reactant we used. We could do so much stuff just by finding the moles of gas for that reaction. So let's try that for the reaction that we just saw. We want to calculate the mass of oxygen produced by the decomposition of KClO3 when 821 milliliters of oxygen is collected over water at 30 degrees C and 1.015 atm. So the first thing that we're going to want to do is realize that this was collected over water at a specific temperature. This tells us that we have to use P total equals P gas plus pH2O to solve for P gas. So the total temperature was 1.015 atm, and at 30 degrees Celsius we can find the vapor pressure of water from our table. So 30 degrees Celsius, we have a vapor pressure of 31.9 torr, right? 30 degrees Celsius, here's temperature, here's pressure. 30 degrees Celsius, 31.9 torr. So we have 31.9, there we go. 31.9 torr. I have to convert torr to ATM, okay, because I can't use torr as my pressure unit if I'm going to use ATMs. So we're going to use our conversion factors from our previous lesson. Where 1 atm is equal to 760 torr. So we'll take that 31.9 and we will divide it by 760. So we get P gas is what we're looking for, and the pressure of the water is 0.0419. We can throw 7 on there, why not? So in order to find the pressure of the gas by itself, we take 1.015 and subtract off 0.04197 to get the pressure of the gas is equal to 0.97303, and that's all in ATM because that was an ATM. There we go. So now we have our pressure of the individual gas, we have our volume, and we have our temperature. So we can now solve for N. We're going to just quickly convert milliliters to liters, 0.821 liters, so that we can use R appropriately. But we get P of 0.97303 times the volume, 0.821 liters, is equal to N, which we're solving for, times R, 0.08206, times the temperature, 30 plus 273.15. So we solve for n by doing 0.97303 times 0.821, and we divide that by R and the temperature. So we get an n value of 0.0321 moles of KClO3 of O2. We wanted to find the mass, so now all we have to do is multiply by the molar mass of O2. 1 mole of O2 is 32 grams. So we'll take that and multiply it by 32. And we get a total mass of 1.03 grams of O2. 3 sig figs there. So that is the mass of oxygen produced from the decomposition of KClO3. Let's do one more. Determine the volume of gas collected over water when 0.501 grams of oxygen is produced by the decomposition of KClO3 at 35 degrees Celsius and 1.08 atm. Okay, so the first thing we're going to want to do, it's collected over water, so let's solve for the pressure. P total is equal to, here we know P total, we'll just write that, we don't need to write the whole equation out. P total is 1.08 atm. We want P gas, so we need to find the vapor pressure of water at 35 degrees Celsius. Water, 35 degrees Celsius, we have 42.2 torr, which we're going to divide by 760 to get atm. So 42.2 divided by 760, just like we did in our previous example, is 0.0555 atm. So we'll use that as our pressure for water. So our pressure of water, 0.055. So to find the pressure of the gas, we do 1.08 minus that pressure of water. So we get P of the gas is equal to 1.0245 atm. Okay, so now we have the pressure of the gas. That's fine. This time we're going to work a little bit backwards. We're given the mass of the oxygen. We now want to work backwards to find the volume of the oxygen. So we're doing the reverse of what we just did. So let's look at what we just did. We had the mass. We're going to use the molar mass to convert to moles. We'll use that and plug it into PV equals nRT and solve for volume. So let's do that. We have 0.501 grams of oxygen, which we are going to divide by 32, so grams cancel and we're left with moles. So we get 0.01565 moles of O2. Now that we have moles of O2 and the pressure of that gas, we can plug that into PV equals nRT, where pressure is 1.0245. The volume is what we're looking for, and we just solved for 0.01565. R we already know, 0.8206 because we're in ATMs, and the temperature is 35 plus 273.15. So we're going to take that moles, 0.01565, multiply it by R, and multiply that by the temperature, 35 plus 273.15. We'll divide that by 1.0245 so that we can isolate the volume by itself, and we get a volume of gas of 0.38627 liters. So typically this would be recorded in a lab setting, and graduated cylinders are measured in milliliters. So we can convert this to milliliters by multiplying by 1,000. And we get, with 3 sig figs, 386 milliliters of O2 gas collected. Okay, so that's our way of using PV equals nRT, as well as our concept of partial pressures, to come together and determine either the volume or the mass of a gas that is collected over water. That completes our last lesson of chapter 11. So please complete your ALEKS homework for this lesson.